Hello, welcome back to your Module 3. So we will now proceed with Unit 3, which is the space trusses. So in your Unit 1 and 2, we discussed about the method of joints and method of sections, which we applied on plane trusses. Okay, so these are now the methods of sections and joints. So we will be now moving to the space trusses. So this is now a 3D truss. Okay, so we will be applying the method of sections and method of joints. Okay. By the way, as I mentioned before, that we can actually use these two methods at the same time. Okay, you can cut, and then that will be a method of sections, and at the same time you can consider a point that is a method of joint. So we can mix this one together. So in this unit, okay, we are going to solve reactions and of course to solve member forces or stresses of determinate space trusses. So we are referring here to again determinate space trusses. So for space trusses, we need to satisfy equilibrium of forces, okay, within, okay, so if we say space trusses again, we need to satisfy equilibrium of forces and rotations, okay, within the three directions, which is the x, y, and z, okay, since of course in plane trusses or plane structures that is only x and y directions. So this time we will now be having the third one, which is perpendicular to x and y plane, that is the z-axis. Okay, so again, equilibrium of forces and of course rotation or moment should be satisfied. But okay, we need to consider this note if we are considering a 3D structure, okay, or especially here in 3D truss or space trusses. So note that moments are taken about an axis. So that is what we are going to do in space trusses or in space structures. If we are taking a moment that is about an axis, unlike in the plane trusses or plane structures that we are taking a moment with respect to a point, but this time this is with respect to an axis. So if we are going to do that, then forces passing through the reference axis have no moments, just like a force passing through a line, okay, but this time we are considering an axis. So a force that is passing or that will intersect with this reference axis will have no moment. Or when do forces intersect? Okay, let's say this is the axis of reference and this is the force. Okay, if that will intersect, if that will pass to the reference axis, then there is no moment arm. So that there is no moment. And in other words, that will only happen if we have a coplanar forces. If the force is coplanar with the axis. Okay, coplanar. They are on the same plane or on a flat surface. And that is also the same if your force is parallel with the reference axis. So if this is the axis and this is the force, there is no moment. Okay, there is no moment. Why? Because of course they are parallel. Unlike on, of course, that is a perpendicular, but there's a certain distance, it is not passing through, then there is a moment. But if that is a, what do you call this one? If that is a parallel, then there is no moment. It will not create a moment because we are getting a moment about, if we say about, around an axis. So this is the axis. So the moment that is only taken by that axis is about its orientation or around its orientation. So that is the important note that we need to consider in space structures, not only in space trusses, okay, but also in, of course, in your space structures. So we need to follow here sign convention. Okay, this is a little bit tricky, especially if you are solving the moments at a certain axis, because of course we have here a lot of directions, 3. Okay, in the two directions x and y, that is simple because of course we are just referring here to moments of any direction. But in here, there will be a time that might be passing through the axis, and there might be a time that will be to the front parallel, but there might also be a time that will be clockwise, counterclockwise, and there are a lot of chances, okay, of these space trusses. So we need to follow here some convention. So consider positive axis as a point of view. So let's say this is your x, y, z. X, and then that is y, and then the perpendicular, which is the z-axis. Okay, the axis going towards you. So that is the z-axis. So the same thing, our sign convention here, the positive is going to the right still, and then going up, still positive. And about the z-axis, the positive there is the one going towards, okay, or inwards. If you say inwards, that is going towards you. If we say outwards, that is going away. So that is the negative, okay, of our assumption for, or our sign convention for the axis. So to the right is positive, up is positive, and then of course going inward, it means going towards you, is the positive z-axis. So consider positive axis as point of view. So if we are trying to view a 3D or a space structure here, then we will try to put ourselves on the view. Or let's say, if we say point of view, we will try to consider a view from the positive axis. So let's say you want to take a plan view, or you want to look downward your structure. Let's say this is your structure. You want to look at the plan view of that, or you want to look at the top view. Then we will not, of course, be looking down. We will consider that our eye is above. So that, since again that is the positive axis, positive y-axis. So that is where our point of view. Same thing here in x. This is the positive, so this is where we will try to imagine that we are looking at the 3D structure in this position. So that is again the point of view. And so with z-axis, if you are looking at the front view, then you will assume that you are looking from this position. Okay, so positive. So that is our sign convention. But actually, it's up to you. If you want the other one, the other way around, then you can use that one. Okay, no problem. You can use that one, as long as you need to stick to that assumption. Because of course, if you will be interchanging this one, then of course that will ruin your sign convention, and you might end up with different or wrong answers because of that. So you need to stick to your assumption. So for the sake of this discussion, we will stick to our point of view to be always at the positive axis. And then now consider counterclockwise rotation about an axis as positive. So this is only for our discussion, but if you want, again, you can consider the clockwise. Okay, you might be used already with the clockwise, just like what we are doing in 2D structures. You can still follow that one, but for me, I'd rather for me in this discussion we will be using counterclockwise, because later on, if we will be having a live discussion, then I might be teaching you a hand gesture to what we call this one, for you to have a guide when it comes to the moments with respect to an axis. Okay, I will be teaching you that one in the live meeting. So for now, I will be considering a counterclockwise, because again, that will be for the advantage of the gesture that I will be, hand gestures that I will be teaching you later on. Okay, so now let's proceed with the force component. Okay, so if you say force component, if again your force is inclined, then there should be component, just like in a 2D plane, isn't it? Or 2D structure. If that is inclined, then there will be component with the horizontal and vertical. But this time we have now the third axis, or the third dimension, which is the z-axis. So in that case, again, in 3D or in a space structure, there are two chances. It's either your members inclined only with a single plane, or that is within x and y axis only, or that's inclined with the x and y together with the z. Okay, if that will lean on another, okay, if that will leave the plane of x and y going towards the z, then there will be a third component. Okay, so that is the first component. If we have again the x and y, we have the z component, if that will lean towards z axis. So how are we going to compute this one? Just like in plane structures, okay, if you want to get the horizontal, then that is the ratio of the horizontal run with the, or the horizontal projection with the length of the member. Okay, if you want to get the vertical, then that is the ratio of the vertical with the length to get the vertical component. Same thing here. Okay, only that we have now three projections: x, y, and z. Okay, x, y, and z projections. So consider this figure here. Let's consider member AB. So we have here a force member AB. Then we need to break this down, maybe so that we will be using that for the summation of the forces x, y, or z. So we need to break this down into component, and as you can see, this is leaning towards x, and then of course it rises towards y, and it leans towards z. So there are three projections. Okay, we have here the px, that's the projection along the x-axis, and then we have here pz, okay, that is the projection along z-axis, and then of course the rise towards your y-axis. So by the way, if you are solving the length of a member in a plane structure, that is simple a squared plus b squared, okay, and get the square root of that to get the length or the c. That is Pythagorean theorem. But in a 3D figure or in a 3D structure, in solving the length within 3 projection, the same thing. Your Pythagorean theorem formula is just extended. So instead of having the 2 square of the leg and the square of the 2 legs, then you will now be considering the square of the 3 legs. So you will be having here x squared plus y squared plus z squared. Submit all of this and get the square root, that is the length. Okay? So of course that is just the extension of the Pythagorean theorem. So in our case here, let's consider the distances as the projections. Okay, so let's say that is px for the projection, or that is the distance inclined along your x-axis. So again, that is just a ratio. The component is just a ratio of the distance or the projection with the length of the entire force. So again, the entire force is the force, or let's say that is, for this example, that is FAB, or that is I'm sorry, that is not AE, that's supposed to be AB. Okay, so that is supposed to be AB. So again, if you want to get the component of this force AB in the x direction, then all you need to do is multiply that one with the ratio of the projection along x with the length. So this is the case. Px is the projection along x, and then L is the length of the member. So all you need to do is get the fraction of that entire force AE to get the x component of that. And same thing with the y and z. All you need to do is multiply the fraction of the projection along that axis with the length to the entire force, of course. So that is the force component. Okay, so again, these are important things for us to consider. We need to follow this one. Okay, so the notes, there are the moments are taken about an axis, and then no moments for a force passing through an axis, or that is coplanar, and no moments for a forces parallel to the axis. And at the same time, we need to follow sign convention. So again, this one is for the purpose of our discussion, okay, for uniformity. But if you want to, you can still use the, of course, other directions as your positive. Okay, so force component, that is how to break down. Now we can have an example. Actually, this is the example here. This is the 3D figure. As you can see, there is the x, y, and z axis. Okay, x, y, and z axis. So we have this space truss. We call this one a space truss. Okay, because this is of course a 3D. So as you can see, we cannot draw here a specific type of support. So for a hinge, for a ruler, and for a fix. Okay, because of course it is 3D. So it is not that simple to what to call this one. Not that simple to identify these types of reactions when it comes to 3D. So it is now represented by the arrows. So the number of arrows actually dictates what type of support is present in that point. So just like here, that is only an arrow going up. So it means it is a ruler that is resisting the, or that is supporting that vertical movement of this point. So in here, that is a hinge, because it only supports the vertical and the horizontal. It does not support the, what we call this one, z-axis movement. So it is just a hinge. However, in your B here, there are 3. So that is what we call the ball and socket. Okay, so it is just like a hinge, but it is now its 3D what we call it, 3D equivalent. Okay, wherein it can rotate in direction, but it cannot move through x, y, and z. It cannot move in these 3 directions. So that is the ball and socket. But in here, that is just a hinge, since it is only restricting 2 directions. So now we can say that there are, by mainly of course counting, there are 6 of the unknown reactions. But don't worry about that, because we have a lot of equations for space trusses. As I mentioned on the discussion before, that we will not be using only here 3, not just summation of x, summation of y, not just summation of moment. We have summation of the 3 forces, and then we have summation of moments in the 3 axes. So a total of 6 available equations for the space truss or space structure. So now let's try to calculate first the reaction. So let's try to apply what we discussed, okay, on the assumptions a while ago here, the moments. But of course, we need to visualize. Of course, you need to practice visualizing a 3D structure, especially in drawing, because of course, if that is a solid, it is simple for us to visualize because you can actually hold that one or you might rotate that one. But in this one, in just a presentation, we cannot. It is not that simple to visualize. Okay, by a drawing representing a figure by simple lines. Okay, so it is hard to. It is a little bit challenging to visualize. But in here, okay, so that we can visualize, we need to know how it looks like on the top view. So this is the top view. We will try to look on the positive. So again, we will try to follow the assumption. We will consider the positive axis as our point of view. So that is our point of view on the positive. So top view, so we will consider the vertical view of that. So we will consider the eye to be on the top. So that is the point of view. So we are looking downwards. So this is the top view. Okay, so as you can see, what we can see here is the 15 that is going towards Z. We cannot see this because that is just a line load. And then what else? We cannot see these reactions, vertical reactions, because of course those are line loads. And then we can only see here your B, Z, okay, and then B, X, which are going towards, of course, with respective axis, and then CX going towards X axis. What else? Of course, these are the dimensions. This is 3 feet each from the middle, and then we have 6 feet each from the middle. So that is the top view, okay, for us to visualize. Now, if you want to look at the front view, so this is just the front view. Now, it looks complicated here, but if you try to look only on the positive view of the Z, then that is the front view, then this is only how it looks like. Okay, the other members are hidden, especially that diagonal here that is now hidden below here. And so with the other the inclined members that is hidden by the front inclined members. Okay, this one, these members hide these two members at the back. Okay, so this is only what we can see, and we cannot see that 15 because that is going towards our direction. So that is just a line, we cannot see that one. And so with your BZ here, so only this 25 we can see. And then of course we need to have a view on the other side so that we can complete the 3 dimension. We will consider the positive of X, so that is the right side view. Okay, so if you are looking at the right side view, the same as the front view, only that the dimension is a little bit different. Okay, this time we are looking on the narrower dimension, the 3 meter from the center. So the same thing, so these two will hide the 2 at the back, and this is hidden because of that below. And we can only see this, okay, perpendicular forces. Okay, so BY, BX, this CY and CX, we cannot see that because that is just a line. BZ, we can see that one. AY, we cannot see that, and we can see this 2, okay, because that is within the plane. So that is how we should visualize, okay, so that we can now later on, it will be a little bit challenging for us to be doing the moments. Okay, so it is important for us to visualize. So now with the help of these views, then we can actually now completely visualize the entire 3D figure. Okay, so by the way, what is required by the problem is to determine the member forces of these trusses or of this space truss. And then of course, for us to go there to the member force, we need first to solve the reactions. That is important, of course. Okay, so now this is where we will be using the summation of moment, because we cannot just use the summation of the 3 forces. Remember, we have only summation of forces X, Y, and Z. There are only 3 equations, and if you are counting, there are 6 unknowns. So we need additional 3 equations, which is coming from the moment. Okay, why is it that there are 3 of the moment? Isn't it in plane there is only 1? There is only 1 moment, equation for moment. You can take that one at any point, but that is only 1, because taking a moment equation in any point will be the same all throughout. But in space, we are getting again with respect to an axis. So there is a moment with respect to X, there is a moment with respect to Y, and with respect to Z. So there are 3 equations from moment, and then there are 3 equations from forces. So a total of 6 available equations of equilibrium in space structure. Okay, so we'll start with summation of moment. Okay, you can consider here at a point and at the same time consider an axis. So again, we need to consider now the assumption that, again, go back here, forces passing or that will intersect that reference axis, or it means coplanar with that axis, doesn't have a moment. And then of course forces parallel to the axis also has no moment. So we will consider this one. We will take advantage of this so that we will cancel out most of the unknowns, so that we will have simple equation for us to solve an unknown at a time. Okay, an unknown in a single equation. So if you will try to consider, let's say in my case, I considered first the point B, but of course again we are taking moment at an axis, so we will consider the y-axis at point B. So we will consider a vertical axis here at point B. So that is where we are taking a moment. So it means that whatever passes at that y-axis at B, or whatever intersects at that axis here, will have no moment. And of course, whatever is parallel to y will have no moment. So in the first place, all parallel to y has no moment. Just like this. AY, that there is no moment. BY, that is parallel at the same time passing through your axis. And then of course your CY, that is parallel. So there are no moments of those vertical, and together with the 25 vertical load, there are no moments with respect to these loadings. Okay, and okay, not only that, your your BX here has no moment also, since that is passing exactly at the axis. Okay, the axis is passing, the y-axis we are considering is passing at point B. So that is the meaning of BY. Y-axis at point B. Okay, and so with your BZ. So this is cancelled, that is cancelled, this is cancelled, this is cancelled, and so with your CY. So the only unknown here that has a moment is CX. And of course, this one is cancelled, so the only force that has a moment is 15. So now this is where it will be a little bit challenging if the force is either clockwise or counterclockwise. But as I've said, I will always consider here. Okay, in this discussion, I will always consider counterclockwise to be positive, because that will be the assumption of the hand gesture that I will be teaching you later on the live meeting. Okay, so counterclockwise. So how do you know that is counterclockwise? Okay, look at this. How do you know that this 15 will rotate with respect to the y-axis here at B, as clockwise or counterclockwise? Of course, consider the point of view that we are talking about. We are taking a moment about the y-axis, so we will try to look. Okay, we will try to have a point of view on the top. Okay, since again positive of y. So again, if you are taking a moment at y-axis, your point of view should be on positive y. If you are taking a moment on x-axis, your point of view should be on positive x. If you are taking a moment in the z, your point of view should be on the positive z. Okay, so of course you know the positive x, y, and z. I already mentioned that one a while ago. So we are taking a moment at y, okay, at y-axis. So we will have the point of view on top. So it means that if we are looking on top, okay, this moment will go, okay, it will turn around this axis at point B, okay, which will go counterclockwise, isn't it? If you are looking at looking down at that figure, okay, you're looking down at that figure, this 15 will revolve around the y here in your point B. It will revolve, okay, and that is going, is that clockwise? No, counterclockwise. Okay, counterclockwise. Looking at the plan view, it goes counterclockwise. So that is positive, because that is my assumption. And this one here, the CX, that will go the opposite, which is clockwise, about the y here at point B. Okay, so that is a little bit challenging, isn't it? Taking a moment with respect to an axis. But once you are used to this, then there's no problem, just like the moment in 2D plane. Okay, so again, the point of view, since we are getting here a moment with respect to y, is the positive y, since that is the, again, where we are getting a moment. So point of view, you should not forget about this point of view. So if that's the case, then counterclockwise is positive again. 15 will go counterclockwise with the y along your B, and then CX will go clockwise, so it goes negative. And then simple algebra, you can calculate that CX to be positive. So it means our assumption here, which is going to the right, is correct. Okay, our CX there, which is going to the right, is correct. Again, same thing. If you will end up negative, that means only that your assumption is wrong. Now I will try to take a moment still at point B, but this time in the x-axis. So this is our reference axis, okay, which is actually collinear with your member AB. So imagine your member AB as your axis of rotation. So whatever is passing there and whatever is parallel to that has no moment. So whatever is parallel to x, which is your CX, has no moment. Okay, that is parallel to x. Okay, so it has no moment. And so with those passing through that axis. So this is intersecting that one. And so with this, and so with that. And so with your A, it is intersecting along that axis. So there are no moments of this 4, including that one, since that is parallel. So the only unknown is your CY. CY. So now again, we are taking a moment at x. So we should put our point of view to positive x. So we are looking from this point here. Okay. So if we are looking from this point here, how will this rotate with respect to this member AB, or with the x-axis along B? So that will rotate counterclockwise, isn't it? We are looking here on this side. Okay, we are looking on this side, and that will go that way. It will go counterclockwise. So BX, okay, will go counterclockwise. I'm sorry, not BX. The CY will go counterclockwise. So that is positive here. And the moment arm, of course, is 6. And then how about what else? What else do we have? This is not passing and that is not parallel. So it has a moment. So the same thing, it will go the same direction with your CY. It will go counterclockwise. So positive 15, and then the moment arm of that, okay, if you say moment arm, that is the perpendicular distance. So the moment arm is 12. Okay, perpendicular distance, that is the vertical distance. And then lastly, your 25. How will that rotate? Okay, how will this rotate with respect to your AB? Your AB is along this one, and that will rotate the other way. It will go clockwise. Okay, again, your point of view is from the positive x. So it will rotate clockwise. So that is now why this is negative in the moment arm of that. Okay, this is the projection. The distance vertical to, perpendicular to that is 3. So your moment arm is 3. And now, all you need to do is simple algebra, negative 17.5. So therefore, our first assumption to be CY as going up is wrong. That should be downward. And then finally, let's take again, still at B. Okay, still at B, but this time the third axis, which is Z. So it means it is collinear with your member BC. So it seems like we are taking a moment with respect to BC. Okay, so whatever is passing there will be cancelled out. So this, all the connected forces in your joint B, and of course in your joint C, will be cancelled out. So the only unknown here will be your A. Okay, this has a moment. And again, we are now taking a moment in your Z axis. So we will have a point of view here. Okay, we are exactly in our position. We are looking towards. We are looking in the front view. So how will this rotate? Okay, how will this rotate? This will go clockwise, isn't it? This is your reference here. This is the axis. And that goes clockwise. So that is a negative. AY times the moment arm, of course, is 12. 6 plus 6. So that is a negative. And what else has a moment? 15 has no moment because that is parallel. And 25, this is the force that has a moment because it is not parallel and it is not coplanar. Okay? So this will go. Okay, this will go. This one, what is that? Counterclockwise. Your AY will go the other one, the other side, or the other rotation, I mean. That is clockwise, but your 25 will go counter. So that is the positive. And the moment arm of that is half, which is 6. So simple algebra, you will have a positive 12.5. So it means our assumption for AY is correct. Okay, don't worry, we will not be checking this one first. Later on, we will apply. So later on, if we will be needing these values, we will carry those with negative. Okay, since I am not yet changing the direction here. So now we are good. Okay, we are good with 3. CY, CX, CX, CY, and AY. So we know all of this. The only unknown is the reaction at your joint B. You can still continue if you want to master the summation of moment. But for me, it will now be simpler to use the summation of forces since I already know the 2 vertical, so I can get the third one, which is BY. So summation vertical, going up positive. So AY, BY, CY. Okay, CY actually is calculated as downward, but I will still consider that to be going up, but we will carry the negative. Okay, and then 25 is the only going down. So that is my equation. Substitute the values of what we know. AY is positive, going up, 12.5. CY is negative. Why? Because it is supposed to be going down. And of course, your negative 25, simple algebra, you will have a positive 30, which means it is still upward. So we know now all the vertical. We can now solve the x, because we already know your cx. Then we can calculate your bx here. Okay. So summation x will be bx is going to the right positive, cx is going to the right positive, and that is the only force along x-axis. But we know that cx is 15, positive 15, going to the right. So if that's the case, then simple algebra, your bx is negative. So it means it is the opposite. So this should be going to the left. And finally, your final bz, which is now summating forces along z, and again, the positive is assumed to be inward. If we say inward, that is going towards us. Okay? That is the positive z. So 15 is going towards us, so positive. BZ is also going towards us. Since again, I always assume that it is going away initially. So now, substitute your 15. 15 is already there. So transpose that is a negative, so that means it is the opposite. So instead of inward, instead of that to be inward, that should be outward. That is going away the point, away from us. So now, these are the reactions. Okay. So again, that is the challenge here. The resolving of reaction is a little bit challenging due to the summation of moments with respect to an axis. But once you are used to this, and of course later on in the live meeting, I will be teaching you the gesture that I know using the hand. If you want to follow that one, if you want to take advantage of that, then better. But if you do not want, if you cannot understand that, then you can stick to our discussion here. Wherein always, okay, put yourself on the positive direction. On the positive axis. So again, if you are taking a moment at x, put your point of view on the positive x. Okay? Then it's up to you if you want to consider clockwise positive or counterclockwise. But for this purpose of discussion, I will consider always the counterclockwise. Okay? So now, again, it is not just enough for us to solve this reaction. Later on, we will be breaking down these inclined members. So we need to know the projections. Or at the same, we already know the projection because of course these are the projections. But what we need to know are the lengths. Okay, lengths of the member. So we need to know these inclined members. Okay, so these four members are inclined in three directions. Okay, x, y, and z. And we have here another which is only inclined in your z and x. Okay, this is your plane xz or zx plane. And that is the only inclination of this member AC. It is not inclined vertical. It is not inclined vertical, So, we have only two components of this, but for this 4, there are three components. So, we need to solve this lengths of the inclined members. So, as you can see, it is symmetrical, isn't it? That the inclination of these 4 along Z are 3 meters all. All of these are inclined 3 meters along Z. Okay, this member and that member are inclined 3 going here, going inward, and then these two here, BE and AE, are inclined away. Okay, within 3 feet along Z, and then they are all inclined again 6 feet along X. Okay, since of course they are all meeting at the middle point, and of course they all rise at the same vertical distance, which is 12 feet. So we will expect that all of these 4 have the same length. So LAE and then LBE and LCE and LDE, these are actually the members. AE, BE, CE, and DE have the same lengths. And again, as I've said, we can only just use here the extended formula of Pythagorean, wherein all we need to do is get the square root of the squares of all the legs. So these are the projections. 6, our projection for X is 6. That is uniform in all these 4 members, okay? And then along Y, that is rising 12. And then along Z, that is going 3. So Pythagorean theorem of this, okay, extended Pythagorean theorem, that is to be simplified as 3 square root of 21 feet. So that is the length of all of these 4 members here. And then we need the length here of this AC. And actually what we only need here is the Z and X projection. So that is 12 and that is 6. 3 plus 3 is 6. So Pythagorean theorem, 6 squared plus 12 squared will give us 6 squared root of 5 feet. Okay? So those are the lengths that we will be needing later on for the fraction of the components. Okay, let's proceed now in calculating the member forces. So, as I've said before, as I've mentioned earlier, a while ago, that we can actually mix together the section of method of section and then the method of joints. But of course, it will be a little bit tricky here in space truss if you are using if you are using the method of section. It's okay if you already mastered the taking of moments with respect to an axis. It's okay. Okay. But of course, since you need to master first the taking of moment with respect to an axis, then I will stick to the method of joints. But if you are already used to getting the moment with respect to an axis, then later on you can mix together this method of sections and method of joints. Okay, so again, for the purpose of this, we will focus, or we will have a pure solution of method of joints. Okay, what we need to do is isolate the joint. So at joint B, so I will separate the joint B. All the members will be represented by assumption initially as tension. Okay, member forces. We have here 3 reactions which are all going. By the way, I already corrected this. Okay, as you can see, your CY is supposed to be downwards. Okay, and then what else? Your BX supposed to be is to the left, and then your BZ is supposed to be outwards. So I already corrected that one here. So your BZ is outwards, your BX is to the left, and then your CY is downward. I already corrected the direction. So I will be using all the positives. So these are the values here. Okay, since I do not have, this will be a little bit complicated if I will plug that one in. So considering your joint B, this is going. This means this is compression, compression, compression. But we will still assume this to be tension. Okay. So if I will try to take a force, okay, this time, of course, we will not be using summation of moment. Okay, what we need here is to summate vertical, since this is a joint. Okay, so we will try to summate force and not vertical, Y. Okay, along Y. So whatever force that has a Y, we will consider that one. 30 is positive, so that is going up. What else? BC is plainly along Z. Okay, it is not inclined along Y. And your BA is also purely along X, so there is no inclination of Y. The only one that has an inclination connected to that is your BE. Okay, this one. So okay, in here I do not have the slope triangle because of course we cannot represent the slope triangle of a 3D. Okay, cannot draw that here. So actually you can, but that will be a little bit complicated, or that will be very, very small here. So I'd rather we'd rather just stick to the formula again. Going back to that, where's that? All we need to do is multiply the fraction of the projection and the length with the unknown or the member force. Okay, so let's go back here. That is the only member that has a vertical component. BC is purely along Z. BA is along X, so only BE. So what is the component of this? How did I get that 4 over square root of 21? Okay, look at this. Isn't it? We calculated that the length of this 4 inclined going to E is 3 square root of 21. We can go back there. This one, 3 square root of 21. And we will ratio that one with the projection along, since we are considering Y, projection along Y. So what is your projection of this member along Y? That is rising 12. So 12 divided by 3 square root of 21, that will be reduced to 4. Okay? The 12 here supposed to be on the top is divided by the 3 together with the square root of 21. We have here 3 square root of 21. Okay? 3 square root of 21. Therefore, the 3 will divide the 12, that will become 4. So this is just the reduced. That is just the reduced fraction of the projection all over the length. Okay? So again, since that is Y, so projection along Y, so that is 12 divided by the length. However, that is simplified. Okay, so simple algebra, that is now BE, and that is a negative 15 square root of 21 all over 2. So negative means our assumption is wrong, so this is supposed to be is compression, not tension. But still, I will not change that one for this figure. I will still consider that direction, but I will carry the negative. Okay, so If you want, you can still consider, or if you want, you can convert that one into the decimal. But I'd rather use this for me to have the exact values. Okay. So again, that means it is compression. Now let's summate forces horizontal. Z along Z. So the positive, I assume positive to be going inward, going towards us. So what are the members that has that direction? Of course, your BC, that is purely, but that is going the opposite. So that is going outward, so that is a negative BC. 15 is going still the same, outward, so negative. And what else? This has no component, only your BE. This is inclined along Z, so there is a component. And again, look at this. This is going away. It is leaning along Z away from us. So that is still a negative. But again, what is the fraction? Projection of Z. Projection is 3. Isn't it 3? 3. So 3 all over 3 is square root of 21. So 3 and 3 cancels. You will only have there 1 over square root of 21. So again, that is just simplified, guys. This is just simplified. But if you want, you can still consider the entire value. And then of course, since we already know this BE, I will substitute that one. But again, it is given that that should be compression. In here, we are using a tension, so we will carry the negative. So simple algebra, that will give us a negative 7.5, so it means the opposite. So BC should be also compression. It will go inwards. So 7.5 compression. And then lastly, summate along X, going to the right positive. So 15 is negative, and then BA, that is purely along X, so negative, going left. What else? This one has, again, since this BE is inclined in 3 directions, then there will always be component in the 3 directions. So projection all over the length. So what is the projection along X? Projection of this is 6. 6. 6 divided by 3 over square root of 21. 3 and 6 cancels. You will be left with 2 on the top. Negative, because it is leaning. Okay, it is leaning, to the left. It is leaning to the left. So that is negative. So simple algebra, your BA, okay, calculate this one. Look at this. That is the good thing if I am using the exact value. Okay, square root of 21 cancels totally. This will become positive. 2 and 2 cancels, so you are left with this as positive 15. Minus 15 will be 0, so BA has nothing to be equated with, so that is 0. Okay. So from this point, we already calculated the 3 members connected to that. AB, BC, and BE. Now let's proceed to another one. Okay, why did I not started with A? Of course, I cannot start here because there are 4 unknowns. If I am going to start with A, 1, 2, 3, 4, and we are only using 3 equations of forces. Okay, we cannot use here again a moment. So we are only limited to 3 equations. We cannot solve this at joint A. So I'd rather start here at joint A. Now I already know this and that, so I can actually go to joint A or joint C. But for me, I want to proceed first to joint C. Okay, joint C. Look at the connections. Okay, in here I will not be writing again the member name of those who we already solved. Okay, so that we will not be confused. Unlike on our previous discussion that I always write the member name. But for now, if we already know, I will substitute that one directly and the correct direction. Okay, we calculated this one, BC, to be compression, isn't it? Compression 7.5. So I already applied that one as going towards point C as 7.5, since that is compression. Okay, and the rest is unknown. So we have here your CA, unknown, that is only inclined along X and Y. X and Z only. It is not inclined vertical. So there are only 2 components of CA. Your CD, that is purely along X. Your CE, the same thing as your BE. Okay, CE is the same thing as BE. It is inclined in 3 directions. Okay, it is inclined along Z, along X, and vertical. Okay, summate vertical, whatever is going vertical. So again, the same thing. Your CE has a vertical. Since again, these are all symmetrical, the inclination and the projections are all symmetrical. The only direction is the different. Not symmetrical. The inclination and the projection are the symmetrical, not the directions. Okay, so what is the projection of CE? Same thing, vertical. We are considering we are summating vertical or Y. So 12 is 2 all over 3 square root of 21. So 12 and 3 cancels, you are left with 4 on top. And CE, do we know that one? No. Okay. And then what else is vertical? That is the only vertical. We do not have vertical for these 3 members here. And CX is not vertical, only your CY. So that is going down to negative. Simple algebra, you will have a positive 35 square root of 21 all over 8, or that is 20.05. Positive, so it means tension. Our assumption, tension is correct. Okay? We already solved this one. Summation Z along Z. This 7.5 is going outward, so that is a negative. Your CA, as I'm saying, there is a Z component of that. Okay? So, if we will try to break this down into the component along Z that is going inward, so that is a positive. And what is the component of that? What is the ratio? Okay? What is the projection along Z of your CA? What is the projection of this? This is 6 meters. 6 divided by the length. What is the length of that? Going back there, what is the length? Length is 6 square root of 5. So 6 divided by 6 square root of 5, 6 and 6 cancels, we are left with 1 square root of 5 only. So again, that is the simplified. CA, it is positive. Why? Because the component of this is going now inwards. And then, plus the component of your CE. Still, there is a component of that CE. Okay, since this is inclined in the 3 direction. So what is the Z projection of CE? Z is 3. This one is 3. Okay, that is going half. So 3. 3 all over 3 square root of 21. 3 and 3 cancels, you are having 1 over square root of 21. So we calculated CE as positive, so substitute that. And then simple algebra, you can calculate CA as positive. 25 square root of 5 all over 8 keeps, or in decimal that is 6.99. Positive, so it means tension. And then finally, summation along X, going to the right positive. So 15 is positive. CD is purely along X, and that is to the left, so negative. The component of CA, there is a horizontal component of that which is going to the left. I mean not horizontal, X component of that is going to the left, so negative. And what is the projection of that? Going along X is 6. I mean 6 plus 6 is 12. 12 divided by 6 square root of 5 cancels, 6 will left us 2 all over square root of 5. Negative because it is going to the left. And then the value of that, okay, we can substitute that one directly. This one, substitute that one directly. And then of course the component of CE, which is the component along X. What is the projection along X? Is 6 divided by 3 square root of 21, so cancels 2 all over square root of 21. And then the value substitute, that one positive, so substitute. And then the CD is the only to the left unknown. So simple algebra, look at this, okay? The square root of 5 cancels, you are left with 50 all over 8. Negative 50 all over 8. 21 and the square root of 21 cancels, you are left with 70 all over 8. Okay? Here is 50 all over 8. This is 70 all over 8. That is 120 all over 8. 120 divided by 8 is, these are both negative, so negative 15. And that is positive, so it will become 0. So CD has nothing to be equated with. So that is 0 force member. Okay? So 0 force member. Now, we already know whatever is connected in your B and in your C. So actually, we completed this one, this. So we completed this. We only have 1, 2, 3 unknowns left. So if you want, you can proceed to A. But for me, I want to proceed first to D. I mean, sige, A. Let's proceed to A, I mean. And later on, we will try to check that one. Because look at this. If we already know all of these members and this one, the only unknown is 1, 2, 3. If we will proceed to A, then we will get the 2 more. So we will only left with this. We can solve that one at joint D. And then later on, we will use your joint E to calculate, I mean to check the value. Okay. So proceed to A. These are now again connected. This is the only reaction, which is going up 12.5. Okay. And then we calculated your AB to be 0. Isn't it? 0 force member yan. That is 0 force member AB. Here. 0 force member AB. Okay. So AB is 0 force member. I will not put there arrow. Of course, for us not to be confused. And then of course you have this AC, okay, only inclined along X and Z axis. So that is already calculated. I will substitute that one so that we will not be confused as another unknown. Okay, so that is according to our value a while ago. Okay, AC is the same as CA, which is 25 square root of 5 all over 8, which is tension. We calculated this one as tension. The only unknown now is your AE and then your AD. Let's start by summating forces Y. So all those with Y. What are the members with Y? Only this, and of course your AY. Okay, so projection of AY is, the direction of AY is going up, so that is positive 12.5, and then the component of AE is going up, so that is still positive, and then the fraction, okay, this is repeated a while ago. Projection all over the length, that will be simplified as 4 all over square root of 21. So we have an unknown AE. Simple algebra, negative 25 square root of 21 all over 8. Negative stands for wrong direction, so that should be compression. Okay. And then now summate along Z. So inward is positive. What are the forces along Z? AD. This one AD is going away, since I assume that one to be tension, so that is negative. What else? So we have a component of your AC along your Z, and we have a component of your AE along Z. So there are two more. So all their components are going away. Isn't it? AD is outward. Component of this is outward. Component of that is outward. So all we need to do is get the fraction. So for AC, the projection is 3 all over 6 square root of 5. So that will be simplified as is that 3? No, 6 all over 6 square root of 5. So 6 and 6 cancels, you are left with negative. Negative since it is away. 1 all over square root of 5, and that is the value of our AC. Okay, that is the value of our AC. And then your AE, that is going away. So again, projection of that is 3 all over 3 square root of 21, so it cancels. You have only 1 over square root of 21 AE, but we know AE to be compression, so we need to carry the negative, so carry that one. So the only unknown is AD. Simple algebra. Look at this again. Square root of 5 cancels, and that will be negative 25 over 8. Square root of 21 cancels, that will become positive 28 over 8. So it will become 0, so AD has nothing to be equated with, so AD is 0. So there are already 3 zero force member that we solved. Your AD, your AB, and your CD. Okay, these 3 here. The CD, AD, and your AB. These are zero force member. We calculated that one. And finally, summate along X. So this will not be included. Your AB will not be included since that is a zero force member. What else? This AC still has a component along X, and then your AE has a component along X. So what are we going to do? Consider that one. So the component of this is going to the right, so positive. That is 2 square root of 5. Substitute that one. And then of course the component of your AE, which is 2 square root of 21. Okay, since the projection is 6. Okay, 6 all over 3 square root of 21, it will simplify to 2 square root of 21. And then again, we calculated your AE a while ago as compression, so I will carry the negative since I did not change the direction. And then look at this, there is no unknown. So this equation is actually one way of checking. Okay, actually, we will not be solving anything from this, but we will rather satisfy the equilibrium for us to know if we are correct or not. That should be satisfied. And look at this, square root of 5 cancels, so this is 50 all over 8. The square root of 21 cancels, this will become negative 50 all over 8, so this will be totally 0. 0 is equal to 0, so we satisfy this one. So that will be an additional confidence to our answer. So there is only one unknown, this one. So it's either you will take it at E or you will take it at D. For me, I'd rather take it at D so that I will use E as my checking point. So proceed to joint D. So this one is the joint D first. This is E, but this is what I used first to calculate the unknown, DE. So look at this. We calculated your DA as zero force member and your DC as zero force member. So what do we expect? There are no forces with that. So even if your DE is unknown, we will summate nothing from that. Okay, isn't it? You can break this down into vertical component and summate y component of that. There are no force to be summated with that. So that is 0. So your ED or DE is also zero force member. Why? Look at this. This is zero force, that is zero force. And there is no load for that to be carried. So it means these are all zero forces. Okay? But later on, okay, I have nothing more to calculate. I already know all the forces, but I am still having 2 more equations left for joint D. I can use that one as checking. So if I will do that, summation Z, okay, look at this, and the component of E along Z is still 0, so of course that will be 0 over 0. So we are okay with that. The same with summation along X. Component of DE, since DE is 0, so there is none, so 0 is equal to 0. So okay. Okay, so now we can proceed to joint E. Again, we are good. All we need to do is to check at joint E. We satisfy that one, then we are 100% sure. So joint E, this is the joint E. It is a little bit complicated because of the different directions, and there looks like inclined in different direction. Okay, but go back here, that is actually the same. Okay, this is only to interpret the direction of the forces. We calculated your AE and BE to be compression, and these are going now towards your point E with these values of the AE and BE. We calculated your DE here to be 0, so that is 0. I am only putting their line, that means there is a member there. And then your CE, we calculated that one to be tension a while ago, so that is going away. And this is the value of that. So include these forces here along the axis, then summate the forces along the 3 axes. We should satisfy all the equilibrium. Let's start with Y. Okay, so all of this has Y. Okay, all of these are inclined in 3 directions, isn't it? So all of them have X, Y, and Z component. So let's summate along Y. So that is the only additional with the components of the 3. Again, this is useless, that is 0. So 25 is down, so negative. So you will separate here. But look at this, isn't it? As I'm saying a while ago, all of these have the same projections. Along X, along Y, along Z. The only difference are the directions. So all their projection along Y is 4 all over square root of 21. Okay, that is again simplified. That is supposed to be 12 all over 3 square root of 21. 3 only divided the 12 by 4. So it became 4. So now the component of this is going up. So that is positive. That's why this is plus. The component of this is going up. So that is also positive. But this is going down. So that is negative. If you want, you can do it 1 by 1. This will be multiplied 1 by 1 if you want. But I'd rather do it this way, since they have all the same projections. And calculate this one. Look at this. You do not need actually your calculator here. Look at this. Square root of 21. The 3 square root of 21 are similar. So we can factor that out. It will cancel with this. Isn't it? And then now you can add this 25 over 8, 15 over 2, and then subtract the 35 over 8. Okay? So for us to make this 8, multiply this by 4. 4, and this will become 60. So this will become 25 plus 60 will give us 85. Minus 35 will be 50. Okay? 50 over 8 times 4. Do not forget there's still a 4 there. 200 over 8. 200 divided by 8 is 25. Minus 25 is 0. Or you can do it by calculator if you want. So we satisfied equilibrium along Y in your joint E. Now let's proceed along Z. Inward is positive. So what is inward here is 15. So positive. Again, as I'm saying, they have all the same projections. So what is the projection along Z of all of this? This is 3 all over 3 square root of 21. So 3 and 3 cancels. You have 1 square root of 21. So inward is positive. Projection of this is away. So negative. Yes. That is negative. And so with this is negative since that is away. This one is also away. Why? Because this is going from this going away. Away. It is not going towards us. It is going away to point C along Z. So it means all of them are negative. Why is this plus? Because I factored out the negative here. But if you want, you can do it again 1 by 1, no problem. Then look at this again, the same explanation. Calculator that one, that will be 15, and then it will be subtracted from here. It will be 0 equals 0. Okay. So this is now along x. So look at this. This is leaning towards positive x direction. So the component of that is positive. This is leaning against, or it is going to the left. So that is negative. This is going still to the right, so positive. So if you will try to submit all of these, that will give us 0, which is equal to 0. We will satisfy the equilibrium. So we are 100% sure that our answer is correct, but of course we need to outline that one, of course, to explain or to visualize. Okay, to visualize, of course, our what this one result. Okay, so look at this. If we will try to apply color coding, okay, these are the values that we calculated. Okay, so there are 1, 2, 3, 4 zero force member. I will color that one as blue, so that will remain blue. All of these blue members are not carrying any stresses. So actually, look at this. All those connected at joint D, since there is no loading at joint D and there is no support here, they are all zero force member. It means they are all useless. So we can, if we will remove this one, okay, we can remove actually this one, then this will still stand. This will still carry the loading. Okay, and then look at this. We have how many compression, tension first? 2. Your CA and your CE. This is color green. CA and CE. So how is that being tension? Because look at this. It is supported here, it is being restricted here and being restricted here. And that is being pulled in that direction. The top is that being pulled along Z. So this will be stretched. Isn't it? This will be stretched. And why is this stretched? Because of the 25. 25 is pushing that one. So this will be forced to split. Okay, these 4 legs will be forced to split. So this will be elongating, these 2 points here will be elongating your AC. So yes, it is reasoned out. And then we have here 3 compression, BC, BC, this one, BC, the pink color, AE, AE, and BE, BE. So why are this compression? Look at this. It is being pushed downward. So we'll expect this to be compression, and at the same time, because of this Z force here pulling that one, all the loads of 25 is concentrated now to these 2 front inclined legs. So these are now being relieved. Okay, the effect of 25 within these 2, and actually this will not be stressed. Why? It is not supported. So that even if there is a result of 25 with this member, that is not resisted. So this is free to move. So it means it is not stressed. But this one, isn't it? Why is that tension? Because of that, it is being pulled by that. This is being compressed, and then due to that one, all the effect of 25 is transformed into these 2 legs here. And why is this compressed? Because this is being pulled. So this will be shortened. Okay, so that is visualizing, of course, visualizing your result of the member forces. So that's it. That is the analysis of space trusses. So again, the challenge here is actually taking a moment with respect to an axis. But the same method of joints, you can take method of sections, but as I'm saying, if you're still having a hard time on summation of moment with respect to an axis, better focus on using the method of joints in space trusses. Okay, so that is the only difference, and of course, due to the 3 directions, the unknowns are more compared to the 2D. Okay. So let's review some concepts. In space trusses, equilibrium should be satisfied in all 3 directions, x, y, z. Okay, equilibrium, we are talking about here summation of forces and summation of rotations. And moments are now taken about an axis. And if that's the case, if moments are taken about an axis, we should not forget that forces parallel to the reference axis is having no moment, and all the coplanar, if you say coplanar again, those force with the same plane with the axis, or it will intersect the axis, has still no moment. And finally, of course, always consider the unused joint, or if you're using method of sections, always use the unused section as a way of checking the previous solution. That is for you to check, of course, the result. Okay, So if you have any question, you can comment below the video, or we will discuss that one during the live meeting. And of course, in the live meeting, I will be teaching you the hand gesture that I'm talking about. For you not to be, you might be needing this one for you not to be confused with the positive and negative of these moments. Okay, so thank you very much for watching. So we will be discussing on the live meetings your questions. Okay.